next we're going to learn how to use calculus to sketch graphs of functions. Now the process we go through will work for any function, but the graphs we'll sketch are those of polynomials, and I will post a few others on Canvas just so you can see what it looks like. I mean, I will test a polynomial, but there will be 6, 10, I don't know, a bunch of graphs you can look at where I go through all the calculus. But first, we need several theorems, all of which are consequences of the mean value theorem. I'm probably going to need a stick. First, if f prime is greater than 0 on a to b, now these are consequences of mean value theorem, so they have to be continuous and differentiable. But I didn't write that because don't worry about it. But they do have to be continuous and differentiable, which everything we do with graphing will be. If the first derivative is positive on a to b, then f is increasing on a to b. If the first derivative is negative on a to b, then f is decreasing on a to b. A consequence of the mean value theorem, and we can see that if we remember what it means for a slope to be positive, going upwards, and if we know what it means for a function to be increasing, well, that's also going upwards. So in this theorem, we have a relation between two upward motions, I suppose you could say. So what does that look like in this first graph? Well, right here, slopes are positive. Why is that shaking? Slopes are positive. Slopes are positive because this is it's going in a positive direction. Slopes are positive. Slopes are positive until it reaches that top point. Then the slopes are 0. But notice, after that point, where the function is decreasing, so the function is increasing here as we go in the positive x direction. And where it's increasing, the slopes are all positive. The slopes of tangent lines. So the derivative is positive where it's increasing, and notice after that it starts to decrease, and all those slopes are negative. And similarly, in this one, until we reach that point, slopes are all negative. Maybe I should do it like this. Slopes are all negative, then it's 0. And then afterwards it starts increasing, and over there the slopes are positive. Now, that's useful, and we're actually going to be able to use that in a moment, but to this point, one of our goals is to use calculus to differentiate between a local maximum and a local minimum. So notice f prime equals 0 or undefined in each case. EACH, that's not even close. In each case. Here's a local maximum, local minimum. But with the visual we just went over, we can use calculus to differentiate between them. Because what happens as we go through that point? Well, derivative is positive. Slopes of tangent lines are positive. Tangent lines are positive until it gets to 0. And then afterwards, slopes are negative. So here we have positive tangent line, positive tangent line, positive tangent line, slope, positive tangent line, until it hits this top point where it goes from positive to 0. And then after that top point, it starts going downhill, which with tangent lines, we see as a negative slope in that one. In the second diagram, if we look at tangent lines, well, tangent lines are negative, 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 until it gets to 0. And then after, the tangent lines become positive, more positive. And this theorem, called the first derivative test, well, the first two parts of it say what I just said. And with this first derivative test, we will be able to differentiate between a local maximum and a local minimum using calculus. First derivative test. Take a critical point. Well, when I was doing this, I said tangent lines are positive. But look over here. If tangent lines are positive, then f is increasing. If tangent lines are negative on an interval, then f is decreasing. Well, this says the same thing. If tangent lines are positive to the left and tangent lines are negative to the right, so with slopes of tangent lines. So if the first derivative is positive to the left of a given point and negative to the right of a given point, then it'll be going from increasing to decreasing. And in particular, when it goes from increasing to decreasing, that will result in a local maximum. And similarly, if slopes of tangent lines are negative to the left and then positive to the right, then that will result in a local minimum. Derivative is negative here, negative, 0, and then positive. And finally, the third part, if f prime, so in these two examples, we went from positive to negative, negative to positive. What if we had a situation where we went from positive to positive or from negative to negative? Well, if f prime has the same sign on each side of a critical point, then f does not have a local maximum and f does not have a local minimum. That says f has neither a local max nor a local minimum at x. And for an example of that, well, for an example of these two, refer to the two graphs I erased. For an example of 3, consider this function. X cubed, let's move it around. X minus 4 cubed plus 7 at x equals 4. Derivative 3x minus 4 squared. Critical point at x equals 4. The graph looks like this. 4, 7, so it looks like this. That might go below. It doesn't matter. It goes, that's 7. Okay, yeah, that's positive. Oh, no, it's negative. What am I saying? That's a 3. So this is not to scale. But notice at this point 4, what do the tangent lines look like? Well, they start being positive, 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 until it gets to 4. The tangent line is actually horizontal, meaning the derivative is 0. So on the left of 4, we have a positive first derivative, and then after 4, we still have positive slopes. So we start with positive slopes, positive slopes, positive slopes, 0 slope at 4, and then positive slopes. So in this case, the derivative is positive on both sides of 4, and there's no maximum and no minimum. And similarly, if it's negative on both sides of 4. Now, we've analyzed the first derivative. This theorem also could apply to the second derivative. How? Well, instead of f prime, you can make it f prime prime. And if you do that, f here would be prime. So just add a prime to everything. Now, if we do that, it might not be perfectly useful the way it's phrased. So let's look at a couple graphs. Before we look at some graphs, I'd like to make the following observation. And I would include the graphs here, but there are 4 of them, and I want one for each board. Remember one of the interpretations of the derivative. The derivative measures a rate of change. So dy dx tells us how y is changing as x is changing, and it tells us how y is changing as x is changing at a given point. And we understand that as slope of a tangent line at a given point. But we want to look at the second derivative, the derivative of the derivative. Well, if dy dx tells us how y is changing as x is changing, then the derivative with respect to x of the derivative tells us how the derivative is changing. In particular, it tells us how the slope of the tangent lines are changing as x is changing. And now, let's look at 4 graphs. These 4 graphs are going to be very important for our graphing. In fact, the graphs we do in all graphs are going to be pieces of these 4 curves. Well, and not all graphs. I mean, lines aren't. But most graphs can be broken down into pieces of these four curves. So let's look at how the slope is changing. Remember, the derivative of the derivative is going to tell us how the slope of the tangent lines are changing. So let's see how the slopes of the tangent lines are changing. Here, it's a positive number. As you travel on this curve, positive number, but notice it's becoming more positive. So it starts here, then it becomes more positive. So as x, and when x changes, we're always going to assume in the positive direction. So as x changes, the slopes of the tangent lines become what? They start as positive and they get more positive. More positive. Do we have a word for more positive? Increasing, maybe? Well, let's look at the next one. And in all of these, the first three lines of that are going to be the same. So I'm not even going to, I'm just going to draw lines, I guess. I don't like having to write words too many times. Let's look at slopes of tangent lines here. What happens here? Well, they start like this. They start as negative slopes. But look what happens. They are still negative. Up here, it's very downward slanted. But it becomes less downward slanted. So here it could have a slope of like, I don't know, -7. But as it goes on this curve, the slope, like here maybe, is like a -1 or a -0.5. So it starts as a large negative and becomes a smaller negative. So the slopes of the tangent line become less negative. Starts at like a -7 and goes to like a -1. Less negative, another way of saying more positive. You know, and with this less negative, more positive, you know, you can just think of the number line. If it goes in the, and if this is the number line, positive infinity, negative infinity, if the numbers go in this direction, they're becoming more positive. And so if you have like -50 and you go to 50, those are becoming more positive. So in both of these cases, slopes of the tangent lines became more positive. What happens in this third case? Well, let's look at slopes of tangent lines. They start as a positive, and then they become still positive, but less positive. Look how unslanted that is. They start as a very positive, very steep slope, and it becomes less positive. So it starts at like a slope of 7 and ends at like a slope of, well, in this case, it looks like it goes almost to 0. So here we will say less positive. And what about this last case? Well, and you might expect something like this. Let's see if our expectations come to reality. Starts as a negative, becomes more downward sloping. Starts as a negative, downward sloping even more. Negative, like a -1-ish. I mean, that's not -1. That's more like -0.5. But it becomes much more downward sloped. So it starts as a negative, it becomes even more negative. And of course, that's another way of saying less positive. In my notes, I have more negative for both of them. It might actually be, yeah, I guess that would make more sense with these. I mean, I have more or less positive here, and you could think of it as more negative. Well, it is more negative, because it's going from large positive to small positive. So keeping everything in terms of mores might be better, so I'm going to erase that. I mean, they are the same, but Now, keeping this in mind, we're going to define a couple terms and then give a result on the second derivative. So we consolidate those diagrams with this theorem definition. If f prime is increasing on A to B, then f is concave up on A to B. If f prime is decreasing on A to B, then f is concave down on A to B. F prime is increasing. The derivative is increasing. Slopes of tangent lines are becoming more positive. The first two of those four, the slopes of the tangent lines did become more positive. So f prime was increasing. So those first two are examples of pieces of graphs, which are, well, I guess they're graphs, which are concave up. And in the last two, f prime is decreasing, f prime is becoming more negative. You go from -6 to -30, you're decreasing. You go from 10 to 4, you're also decreasing. So if f prime is decreasing, then f is concave down. Those last two, where the slopes of tangent lines were becoming less positive, were becoming more negative, were examples, or are examples of functions which are concave down. And we're going to talk about that a little bit more, but first, we have a second derivative test which parallels the first derivative test. And again, all of these results are consequences of the mean value theorem. In particular, that first theorem we wrote in this video. Second derivative test. So the first derivative test told us about local maximum, local minimum, and increasing and decreasing. The second derivative test is going to tell us about concavity. Because the concavity is a result of looking at how the derivative is changing. So it's looking at the second derivative. 1, if f double prime, second derivative, is positive on A to B, then f is concave up. If the second derivative, f double prime, is negative, then f is concave down. And we're going to look at a couple more graphs and interpret them, and then we'll do some actual examples. But first, with this, so with the first derivative, where it went from increasing to decreasing, that was a convenient point, a local maximum or a local minimum. Or, well, yeah, local maximum or local minimum. Where concavity changes, in other words, where the second derivative goes from positive to negative, possibly, is useful. So we have this definition. If f is continuous and x changes concavity at x, then we say f has an inflection point at x. And I'm going to illustrate this definition with two examples, one where it is continuous and one where it's not continuous, but concavity changes. So example of this definition is something that looks like, say, this. In a moment, it'll become more clear why concavity changes. But you could do a slopes of tangent line argument, but it might be a little tedious without the visual I'm going to do after this. But right here, concavity changes. Oh, what the? I'll just tell you. Concavity is concave down because the caved-in portion is pointing down. Concavity is concave up here because the caved-in portion is pointing up. So at this point, concavity changes. So this, at that x value, concavity changes. So we'll call this an inflection point, INF point. That's if it's continuous. Let's say inflection point since concavity changes through that point. What about and continuous? That's the entire point of these two examples. Inflection point since concavity changes at that point, and it's continuous at that point. What if we had one like this? So you could take something like 1 minus, or 1 over 3 minus x, or 1 over 2 minus x, at 2. Well, right here, I will tell you this is concave up because that's pointing upwards. This is concave down since that's pointing downwards. Let's just call it x. But it's not continuous, so this will not have an inflection point at x, even though concavity changes. no inflection point, even though concavity changes at x, I guess I'll say. So right now, so far we've had several results, and the results, just phrasing the results, you have to be very careful with the phrasing. But fortunately, all of these results we've covered so far in this video can be reduced to 4 graphs. Observe. The sketch of a graph can be found by identifying intervals over which the graph looks like one of the following and piecing together the result. And what we're going to do is use the first and second derivative tests and the theorems that we've covered and step all over the microphone. So let's look at each of these graphs in terms of the first and second derivatives. Well, the first derivative told us about the function increasing and decreasing. So what's this function? In each of these I'm going to write like 4 things underneath, so you know. This function is increasing. F increasing. It's going up as x gets positive. This one is also increasing. I mean, it's increasing more slowly, but it's still increasing. It's going up. How about this next one? Well, that's going downhill. Means it's decreasing. So I guess we'll first observe these with words and then with calculus. And this one, also going downhill. Much faster, too. Why is he saying much faster? Okay, what about concavity? Well, so right here we have positive slopes of tangent lines, and they become more positive. From that, you can conclude that F is concave up. CC arrow up. Another way, an easier way, I would say, to show that is by looking at the caved-in portion and just drawing an arrow away from the caved-in portion. If that arrow's going in an upward direction, then F is concave up. And over here, you looked at the caved-in portion, draw an arrow away from it, it's going down, and F is concave down. Here, alternatively, the slopes become less positive. Yes, less positive. Over here, caved-in portion pointing in an upward direction. And over here, caved-in portion in a downward direction. So we have F is increasing, increasing, decreasing, decreasing, concave up, concave down, concave up, concave down, with these 4 drawings. How can we interpret that using derivatives? Well, we use our previous theorems. If F prime is positive, then F is decreasing. Then F is increasing. F prime positive. Decreasing, we have F prime negative. Decreasing, we have F prime negative. And here, concave up, remember, went with the second derivative being positive. And this is a nice, I think it's a very consistent result because we have all of these positive sounding words going together. Increasing, up, positive, positive. That's nice. Decreasing, up, negative, positive for that third one. And if the second derivative is negative, then if the function is concave down, the second derivative is negative, and we fill that in over here as well. Decreasing down, negative, negative. So our goal is going to be to identify intervals on which the first derivative is positive and the second derivative is positive, and the negatives as well. I could have said that much better. So let's look at a couple examples. Let's do these 2 examples. Sketch a graph of each function. So you will be tested on a polynomial, likely twice, likely once this week and the final. But definitely look at the document with several other graphs. I mean, you don't have to look at all the d's. Some of the derivative computations and simplifying them equal to setting them equal to 0 get pretty rough, but I would recommend looking through them and observing that all of those graphs are just the previous 4 graphs put together, and with some asymptotes in some cases. But you will be tested on a polynomial, so let's do 2 polynomials. X cubed minus 6x squared plus 9x plus 30. Well, we need where the first derivative is positive, where it's negative, and where the second derivative is positive, and where it's negative. So let's find the first derivative. 3x squared negative 12x positive 9. Well, if we want to find where it's positive or negative, let's find where it's 0, and then look at the intervals that that produces. Take out a 3. Hope that it factors. It does. X minus 1, x minus 3. This equals 0 when x equals 1 or when x equals 3. And we'll do polynomials, so they're never undefined, the derivatives. But in general, you would also have to find where they're undefined. So this first derivative is 0 at 1 or 3. Well, that tells us, if we look at a number line and mark off 1 and 3, the first derivative is 0 at 1 and 3. So everywhere else, it's not 0. So between 1 and 3, it'll be always above 0 or always below 0. Between negative infinity and 1, it'll always be above 0 or it'll always be below 0. Between 3 and infinity, the same. It'll always be above 0 or below 0. So what we need to do is find the sign of f prime in each interval. And we can do that by choosing a single point and looking at f prime. A single point in this interval, notice we're not choosing 3 because we know the derivative is 0 at 3. We're looking for its positive. So if you pick a sample point like 4, put it into the derivative, I don't want to do that computation. Put it into the derivative and look at the sign, because remember, the sign is all that matters. We have a positive then. If we substitute 4, positive times a positive times a positive. What if we choose a number between 1 and 3? 2. That's a good number. That's an okay number. 2 is between 1 and 3, though. Substitute into the derivative. You get positive times negative. 1 negative. Substitute a number here from negative infinity to 1. I'll choose 0. I mean, I like 0. 0 is a good number for substitutions. 0, you substitute up here, you get positive 9. I'll stick with the factored form, even though it's harder in this case. At 0, positive times negative, which is positive. Well, we have where the first derivative is positive and negative, so let's just interpret that. Where it's positive, the function is increasing. Where it's negative, the function is decreasing. And let's keep that in mind. Because when we piece together the graph, we're going to need that. But we also need other information. We need the same information about the second derivative. So let's find the second derivative. 6x minus 12. We want to set this equal to 0. 6x minus 2 equals 0 when x equals 2. That says when. When x equals 2. So that's the only point we need to consider, 2. So over here, the second derivative will always be positive or negative. And over here, it will always be positive or negative. Choose a point here. Say 3. Substitute there, you get a positive. Take a point here. Say 0. Substitute there, you get a negative. Second derivative positive, concave up. Second derivative negative, concave down. Well, these two number lines now tell us everything we need. I'm just going to look at this graph to make sure I draw it semi to scale. I just need to know how high and low it goes. Well, I'll try to fit it on this board. Let's see how it goes. No. I'm going to do this. I'm just going to draw this down here. Okay, so all the second derivative information we needed is now down there. So now I'll be able to draw this graph across these two boards, which will be much better. Now, when actually piecing together the graph, what I like to do is draw a Cartesian plane. It won't always be exaggeratedly taking up the first quadrant, but notice here, the relevant points are 1, 2, and 3. Those are the points where we're going to change from one piece to another. So let's just mark off 1, 2, and 3. Maybe I'll even put numbers this time. Well, that's great. One other thing that will tell us information that will help us draw an accurate sketch is the y-intercept. And with polynomials, that's easy enough to find. Substitute 0. Remember, a y-intercept occurs at a point like that. What's the ordered pair for that point? Over 0, up something. Over 0, x is 0, substitute x equals 0, you get 30. I'm going to label it up here. So label the y-intercept, because without a point on this graph, you don't know if it's like way up here or way down there. Okay, now what? Well, we follow our number lines. I'm going to erase all this work. I don't even want to see this anymore. Follow the number lines. First relevant interval, negative infinity to 1. What happens on that interval? Increasing, concave down. What does increasing concave down look like? Increasing and concave down was the second piece on that list of 4. It looks like that. So from negative infinity to 1, we're going to draw that and going through that point until we get to 1. Great. Next relevant interval, 1 to 2. 1 to 2, what happens on 1 to 2? Decreasing. 1 to 2, concave down. What does decreasing concave down look like? Yes, that's decreasing and concave down. So we draw that from 1 to 2 until we get to 2. I'm probably going to have to move my x-axis at some point. Now, whatever. It doesn't have to be 0. Notice we already have some useful information. We have the local maximum right there. Next relevant interval, 2 to 3. What happens on 2 to 3? Decreasing, concave up. What does decreasing concave up look like? Concave up, decreasing. That's an awful drawing. Decreasing, concave up looks like that. So we draw that from 2 to 3. I'm going to just draw it like that, I guess. And notice in that, we also produced an inflection point. Maybe I'll even label these. Local, maximum, inflection point. Why not label them as we do it? And our last interval is 3 to infinity. What happens on 3 to infinity? Increasing, concave up. Looks like that. It's the only one I remember immediately. So it looks like that. And that produced a local minimum. So a sketch could look like this. Definitely find a y-intercept so that, I mean, if you don't have that, maybe you'll start like down here and go like that and something. This graph is where? What's that ordered pair at 3? Oh, I didn't label it. ordered pair at 3 is 27 minus 54 plus 27 plus 30. Yeah, okay, this is horribly not to scale. Because that should be on the same line as 30, but that's okay. The calculus in there is fine. Let's look at the second example. Now, we actually could graph this with our completing the square method from week 1, since it's a degree 2. Let's use calculus to do it. Let's see what that looks like. First, second derivative. I'm going to do the first derivative here and the second derivative there, so no, I'll just do it here. F prime is negative 4x plus 5. We want where that's 0 equals 0 when x equals 5/4. Add 4x, divide by 4, or subtract 5, divide by negative 4. Well, that's our only point. So let's look at this side. F prime at 0, positive. Let's look at this side. F prime at, I don't know, 2. Negative 8 plus 5, negative. The actual numbers don't matter for these signs. The numbers that matter are where it equals 0. All that matters for these portions is the sign. Well, that's great. We did some of our work. Now we have to do the second derivative. What about the second derivative? F prime is negative 4. Where is negative 4 0? Never, for real numbers. Negative 4 is never 0, but what does this tell us? The second derivative is negative on every point, or at every point the second derivative is negative. You substitute any point in there, you get a negative. You get a negative 4. What does that tell us about concavity? Remember, the second derivative tells us about concavity. This tells us f is always concave down. Well, now we just have to piece together a graph. Let's find the y-intercept, negative 2. So I'll mark that like this. Let's mark off the relevant point, 5/4, and then piece together the graph. On negative infinity to 5/4, what happens? Increasing, concave down. Increasing, concave down. Yes, looks like that. It goes through this point. So it looks like that. And from 5/4 to infinity, decreasing and concave down. Looks like that. So this function looks like this, and we have a local maximum at that point, and this is f. So try these graphs with polynomials, but definitely look through the supplemental graphs that you will not be tested on. I mean, it's nice to see in those all of these 4 pieces, and it's I wouldn't recommend it so strongly if I didn't think you could take a reasonable amount of value from looking at a bunch of graphs you're not required to know.